Alright, the pH scale. This is a scale that tells us how much hydronium there is in the water. These concentrations vary through lots and lots of orders of magnitude, and so that makes these numbers a little difficult to work with. So what we're going to do is we're going to use a logarithmic scale here. That's one that just tells us the order of magnitude, and that'll make the numbers a little easier to work with. So remember I said that in neutral water, H2O will react with another H2O to produce H3O plus and OH minus. And this will happen about 1 in 10 million amount of the time, or if I want to express this as a power, 10 to the negative 7 amount of the time. Then we say that instead of looking at this big ugly number, we look at just the order of magnitude, and that's what sets the middle of our pH scale. So the middle of our pH scale is 7. Now we can see that this varies through huge ranges of numbers. For example, if I added some HCl in, and I added something like 0.1 molar, then that would react with the water to produce H3O plus, and because it's a strong acid, it would react completely, and it would raise this naturally occurring population from 1 in 10 million to 1 in 10, right? This is 1 over 10. And if we express that as a power 10 to the negative 1, we can see that that creates a pH of 1, and that sets the acid end of our scale. But also, we can see that these numbers are really different, right? 0.000000001 versus 0.1. These two numbers are so different, we need a better scale to compare them. So 7 to 1 is much more manageable for people who aren't scientists. One more time here, imagine putting NaOH in, and then those OH minuses that are created reacting to drop the hydronium population. So we put a bunch of this in, and then it used up this, and so what it used to be 1 in 10 million dropped all the way down to say 1 in 10 billion. So some terrible number, and that would be 10 to the negative 10, and so this is a base, and in here we would just use this number again to say bases have pHs that are greater than 7. So 7 for the naturally occurring 1 in 10 million, or 10 to the negative 7. If we increase the hydronium to 10 to the negative 1, an acid, 1, and if we decrease the hydronium by adding hydroxide, say down to 1 in 10 to the negative 1 in 10 billion, then we would get a pH of just 10. So that sort of sets it up, and we can see why we're doing it, because these numbers are not really usable in terms of trying to communicate with the general public. So the pH scale really is just a logarithmic scale that represents order of magnitude, but really it's just to make the numbers easier to work with. How do we do this mathematically? Well, pH is equal to negative log of the hydronium concentration. Or, if I want to use the pH to get the hydronium concentration, hydronium is equal to 10 to the negative of whatever the pH value. In neutral water, 10 to the negative 7, we get a pH of 7. In acidic water, where we have a high concentration, say 1 in 10, instead of 1 in 10 million, or we could express that as 10 to the negative 1, we get a pH of 1, so that represents a high concentration. And in really basic water, 1 in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, whatever that number is, representing 10 to the negative 14, or a pH of 14. this hydronium population being driven down to this tiny number by the introduction of hydroxide into the water, reacting up that hydronium as discussed in the previous video. So this is a little bit weird. 7 is normal, 1 means high, and 14 means low. So there's a little bit of resulting confusion here because my low number actually means high concentration, and my high number actually means low concentration. That's because they are the exponent on a number that's in the denominator. So as the denominator gets bigger, the actual number gets smaller. So that's what the pH scale is. That's how we use it. And that's why naturally occurring water with its natural ionization rate gets a pH of 7. When we increase the pH, the concentration of hydronium, the pH actually goes down. So 1 to 7 represents acids, high hydronium concentration. Seven represents neutral substances, normal hydronium concentration. And 7 to 14 represents bases, which have high hydroxide, causing low hydronium populations. That's the pH scale. I'm going to do another video now where I show how to use these two equations. I know I sort of skipped over that.